So today we are starting the stereoisomerism, and we know that stereoisomer is having the two sections. That first section is called geometrical isomerism and other is called optical isomerism. So in today's lecture we are going to cover the geometrical isomerism, and in the next section we will do the optical isomerism. So let us understand what is the meaning of the geometrical isomerism. So geometrical isomerism, basically it's a stereoisomerism where isomers differ only in orientation of the atom in 3D. So such type of isomerism is named as geometrical isomerism, and we have to learn it that what type of condition is needed for the geometrical isomerism. So let's start with the condition for geometrical isomerism. First condition is a restriction and rotation. Means molecule cannot rotate, like for example double bond. It has the one sigma and one pi, and pi cannot rotate. So that is the fix in the 3D space. Similarly in the ring also, these carbon is in restriction and rotation, even this also. If you try to rotate the bond, that ring will break. Carbon can connect with the oxygen. So anywhere if you are finding the double bond is present, means restriction and rotation can be present. Second is, we need a different substrate or different atom along the restricted carbon. So like for example, if I write these two conditions, so carbon double bonded carbon which we have here, it must have the different substrate. Different substrate means along the double bond these two carbon are in the restriction. This may have the X and Y. The second number also can have the X and Y. Even it could have the P and Z also. So it could be different. The same should not be there, and even in the both the sides should be different. So these two conditions are very much necessary for showing the geometrical isomerism. Similarly, you can show in the ring also, like this is let's say 1, 2 and 3. So I can make it the different substrate, hydrogen and chlorine, and here that hydrogen and chlorine different substrate is there. Similarly here also, if suppose I'll write hydrogen and methyl group, but oxygen have the two lone pair. So this consider as the same substrate, means there is no GI. Remember that different substrate is very much necessary. So this can be possible if it is connected, let's say hydrogen and chlorine and hydrogen and chlorine. Then you can say the geometrical isomerism is there, otherwise no. Similarly in this pattern, here I can make it A and B, and nitrogen have the lone pair. Here could be A or B or maybe C, anything, but it should be different. If it is same, the GI is not possible. So for example, if suppose I'll write ethene CH2 double bond CH2, the first condition is satisfied, but the second condition got failed because of the same substrate. So this is not showing the GI. But if I write like that way, carbon double bond carbon, and here I'll write that methyl group hydrogen and methyl group. So we have a different substrate with the restriction and rotation, so we could say the GI is there. So let us understand the few nomenclature behind the geometrical isomers. Case 1 I am writing, if suppose carbon have the double bond and it has the different substrate, for example hydrogen chlorine and hydrogen and chlorine. So same type of molecule, if it is coming on the same side, so the name of the molecule is called cis. If they are going on the opposite direction like this, then the name of this molecule is called trans. These are the geometrical isomers name. So we have a second example where carbon is held by the nitrogen. Here is a lone pair. There is hydrogen and OH. We can see different substrate are present. So in that case, this is the geometrical isomers, and then name we will write SY and SYN. When the hydrogen and OH that on the same side. But when the hydrogen and OH on the opposite side in the CN bond, then it named as NT. So all are the geometrical isomers, only the name change is happening. So when the carbon is connect with the carbon, you can use the cis and trans. When carbon connect with nitrogen, you can use the SYN and NT. Now third possibility I'll write, if the nitrogen is held by the nitrogen, let's say it has the one lone pair, it also has the one lone pair. I can put any other substrate, let's say phenyl ring. So when we have the lone pair on the same side or phenyl on the same side is look like a cis, so still we will write as a SYN only. The name is changed for the nitrogen compound, and here opposite if I place, then the name is become NT. Similar pattern I can show in the ring also. If suppose same side the substrate are coming, like for example OH and OH, it's called cis. This is the carbon chain, and if the opposite side solid line means toward you, and dash line means away from you, so opposite direction, so the name is become trans. We can write other pattern also, like suppose if I am making this 6-member ring and here we have a hydrogen and chlorine and here we have a hydrogen and chlorine. This also can show the geometrical isomers along this center to this center, restriction and rotation. Not necessary you should have the adjacent one like this case. This is the adjacent one, this is non-adjacent one. Here also the cis and trans possible. If I try to draw the solid line means the same side, so it could be cis, and other pattern could be trans. This could be trans. Hydrogen is optional to put, so one is cis and other is trans. One more, the special case is coming. If the carbon is greater than equal to 8 in cycloalkene, only in that case that GI is possible, otherwise no. If the carbon is lesser than 8 in cycloalkene, the geometrical isomerism is not possible. So this is considered as a you can learn as an exception or special case. So like for example, so we have a total carbon here. So if I write like that way, it's become cis, then it's possible. But if I say double bond like this and say that GI is possible, so no GI. Remember that this is the exception or special case. Carbon is greater than 8 in cycloalkene, only in that case GI is possible. If it is lesser than 8 in cycloalkene, no geometrical isomerism. Properties of cis and trans. So the first one is coming is stability. Trans is more stable than the cis because of the better arrangement, more symmetrical. Second, dipole moment. Here the cis have the higher than the trans. So here the dipole moment means polarity measurement. Here the equal and opposite, it's a vector quantity. So the dipole moment of polarities become 0. But here it's additive. So it goes like that way. So mu is not equal to 0. Mu is a symbol of the dipole moment. So cis have the higher than the trans. Third, melting point. Here the trans, due to the more symmetry, it has the higher melting point than cis, where the boiling point, since more polar character has appear in the cis, so that's why cis have the higher than the trans. So these are the very crucial property and very important. It's just a reverse. So you have to just make sure while marking the right answer. They have the different chemical property also, like suppose if I'm writing C double bond C and we have a COH and the COH, H and H. So we can see here geometrical isomerism is possible, and this is called malic acid, which is the cis pattern where C double bond C, COH, COH, H and H. This is called fumaric acid. So they both have the different chemical property. However, this is the cis form and this is the trans form. So if I'll try to heat up this, we will get the anhydride. But when you try to do this, there is no reaction. So we could say the cis and trans having the different chemical property too. Now we will talk about the number of geometrical isomers. So we have formula for this. So case 1, when the molecule is fully unsymmetrical, then in that case number of geometrical isomers would be is equal to 2 to the power n, where n is represent the number of double bonds or the restricted carbon. So like for example, if I write like that way, so here we can see this double bond have the geometrical isomer. This side is a methyl group and other side is a hydrogen, and this side we have a ethyl group and this side is hydrogen. So we could have the geometrical isomers here. So the total isomers could be is equal to 2 to the power 1. Answer is 2, means one can be cis and other should be trans is possible in this molecule. Trans, and that could be cis. This side is ET and these two hydrogen are that side. This is cis pattern. Now let's move to the case 2. If the molecule is unsymmetrical. Okay, the meaning of the symmetry or unsymmetry. Unsymmetry means the both the ends are different, but symmetrical means the ends are same. Like for example, if I write CH3, then CH double bond CH, and then here CH double bond CH and CH3. You can observe the both the side is the same symmetry. So in that case, the number of geometrical isomers would be is equal to 2 to the power n minus 1 plus 2 to the power the n dash minus 1, where n dash would be is equal to n by 2 if n should be the even double bond. So this case is possible if the n is even, if n is even. So next we have if n is equal to odd double bond. So here we have a even, now we are writing the odd. In that case, n dash would be is equal to n plus 1 by 2. So for example, CH double bond CH. So it has the symmetry and odd also. The number of double bonds are odd where the geometrical isomerism is possible and the symmetry is also there. Remember that the second case is only and only valid when the molecule is symmetrical. So in that case, number of geometrical isomers would be is equal to 2 to the power n minus 1 plus 2 to the power n plus 1 by 2 minus 1. This n dash I put it here. So 2 to the power 3 minus 1 plus 2 to the power 4 by 2 means 2 minus 1. So you got it 2 to the power 2 plus 2 to the power 1. Your answer should be 6. So that's how we can calculate the number of geometrical isomers. And now we have a few questions which is related to the JEE PYQs. So we have to identify which one is not showing the geometrical isomerism. So I am going to write the few example: propene, butene 2, chlorohexane, 1,2 dichlorohexane, 1,3 dichlorohexane, 1,2 dichloropropane, 1,1 dichloropropane. We have to identify which one is showing the geometrical isomerism and which one is not. So you can observe the CH2 group is there, and here is a C methyl group and H group. So this carbon have the different substituent, but this carbon does not have. So we can say no GI is there. In that case, this carbon have methyl and hydrogen. Even this side is methyl and hydrogen. We can have the geometrical isomerism here. In this case, we have a one carbon where it is a chlorine, but rest are the carbon having the CH2. So everywhere you don't have the different substituents, so no GI. In that case, this carbon and this carbon is having the restriction rotation, and we have a chlorine same side. So we could say here the geometrical isomerism is possible. Even 1 and 3 have the different substituents, so we can say the geometrical isomerism is possible. Remember that ring at least the 2 center we needed where the restriction and rotation and different substituent should be there. If it is showing only on the one carbon, it's not possible. Here it is also possible, that is the 2 restriction in carbon and the chlorine different substituent, and related is hydrogen is there, cis and trans both are possible. Now you can see here in this carbon have the 2 chlorine, so same substituent, no geometrical isomerism. So we have to identify here also geometrical isomerism is there or not. So in cycloene we learnt it carbon must be greater than equal to 8, only in that case GI is possible. So we can see everywhere is a carbon 6, so around the double bond there is no geometrical isomerism at all. But we can see with the other carbons. So here all the carbon have the same substituent, here also the same thing. Here we can see this carbon is a restriction rotation and have the different substituent, the methyl and hydrogen and methyl and hydrogen. So around this center we have a GI, but this double bond does not have the GI. Now in this question we have to identify the number of geometrical isomers. So number of geometrical isomers, we have a formula. Here first check which double bond is showing the GI. So this double bond have the same substituent, so this double bond is not showing GI, but this will show because of the different substituent. So we have 2 to the power 1 means 2, one cis and other is trans is possible. Along this double bond GI is possible, different substituents, so this should be 2 to the power 1 and that should be 2, cis and trans again is possible, and both molecule are the unsymmetrical. This is also unsymmetrical, and both the double bond are showing the geometrical isomerism. So we have a 2 to the power 1 means 2 to the power 2. So answer should be 4. So we could have cis cis, cis trans, trans cis and trans trans. These are the 4 possibility we have. In this center also 1 and 1, we have a 1 is stereo center means 2 to the power 1 is restricted carbon we can consider. So that should be 2. Means cis and trans here also possible. So we have now E and Z nomenclature. How we can do that E and Z nomenclature? Remember that this is valid when all the 4 substituents are different, like chlorine, bromine, iodine and fluorine we have. In that case, we are not able to use the cis and trans, so we have a special nomenclature that is called E and Z, where these are the German words, and E stand for the antigen, which means opposite, means trans, and Z stand for the Jusamen, which is stand for the same side. So here we have a special rule that is called the CIP rule, named as Kohn-Ingold Prelong rule, and this is based on the atomic number, or if the atomic number are same, then we can check with the mass. So like how we are going to apply the CIP rule, which is based on the atomic number, let's see here. So first check the GI is possible here along this double bond or not. So we can see restriction and rotation and different substituent this side, chlorine and bromine, and iodine, fluorine, completely satisfying by these 2 conditions. Now CIP rule is telling give the priority based on the atomic number. So let's compare chlorine and bromine. The bromine have the higher atomic number and chlorine have the lower. Here iodine have the higher and fluorine have the lower. So based on that we have given the priority. Now let's see 1 is coming on the opposite direction here and here, trans, so that should be E form, it's antazine. If suppose I'll write like that way, C double bond C, we have chlorine and bromine, and here fluorine and iodine. I just reverse it. Now let's put the priority. Bromine is having the better priority over the chlorine because of the atomic number. However, you can use the mass also, but rule is based on atomic number. Then we have a iodine here and fluorine is here. You can observe 1 is coming on the same side and 2 is also coming on the same side. So we have a trick also, like 2 से 2 को match कराओ, 1 से 1 को, and this look like a Z. So this is called Jusamen, means syn pattern, cis pattern. We can do few more example, like C double bond C we have, and here we have a OCH3, and here we have a O and H, and here we have C triple bond CH, and this side C double bond CH2. So let's see which double bond have the geometrical isomerism. So this double bond is not showing GI, but this is showing, and all the 4 substituents are different, and we have to write the name whether it's a Z form or E form, because cis and trans तो possible नहीं है यहाँ पे. So CIP rule is also suggesting that you have to go 1 by 1, like here is oxygen, here is oxygen. You cannot count the total atomic numbers. You just need to go the bond by bond, means 1 by 1. Oxygen, oxygen common. Now next connection is carbon. Here next connection is hydrogen. Carbon have the higher atomic number. This will have the higher priority over this. Now come to this side. Carbon, carbon common. Now the priority we will give to the multiple bonded. Multiple bonded here 3 times bonded. So how we can mark it? This carbon is actually connecting with the 3 carbon altogether. And here this carbon is connected with the 2 carbon altogether. So obviously 3 have the better priority compared to the 2. So remember that if the multiple bond are coming, you have to count that many times. Triple bond coming 3 times count करना होगा. Double bond coming 2 times count करना होगा. Total count नहीं करना है, 1 by 1 जाना है. Now 1 is on the same side, so we can say it's a Z pattern. We'll write one more example. We have C double bond O and H. We have N nitro group. We have C double bond O and OH group, and we have CH3. So basically I wrote it C double bond C, CHO, nitro group, and this side is a COH group, and this side is a CH3. Why I wrote these all structure? Because we have to count the atomic number according to the bond only. So let's do it. Let's do one more example. C double bond C, we have a CHO, we have COH, we have OCH3, and we have nitro group. To write down the name, we have to write the structure to give the priority. So I'll write here C double bond O and H, C double bond O and ONH, and this side is OCH3, and this side is nitro compound. Remember that while giving the priority, you have to check 1 by 1 only. This double bond is showing the GI. We can find the E and Z pattern along this double bond only, where this double bond and that double bond is not playing any role in the geometrical isomerism. So that carbon same, double bonded get the high priority, oxygen double bonded oxygen, same priority. Now here is hydrogen, here is oxygen. This is first priority, this is second priority. Here you check We have a oxygen and we have nitrogen. Now oxygen have the higher atomic number than the nitrogen, first priority, this is second. So you can observe I am not calculating the total one, I am calculating bond by bond. Now here we have a 1 opposite side, 2 opposite side, means this is the intergen form, E form. So this is all about the geometrical isomers. Next part we are going to do the optical isomers. Thank you for watching CHEMTIDE. Hope you like it. If you find any difficulty, you just let me know in the comment box. And the stereochemistry means optical isomers is coming in the next part. Thank you.